Hello, my name is Roy Simpson. I'm an instructor of mathematics at Xintercepts River College in Sacramento, California. This is a lecture for intermediate algebra on graphing parabolas. I already have a lecture on graphing parabolas that if you're watching this in sequential order through one of my playlists, then you've already known my method or been introduced to my method on graphing parabolas. I'm going to reintroduce it here, but also spend a little more time getting all the details out of graphing and parabola rather than just the basics. We're gonna get as much as we can out of graphing and parabola in this lecture. Specifically, we're going to talk about how to know or how to find the x-intercepts, and also how to know how many x-intercepts there actually will be. What we're going to do is start by recalling the common sense method to graph a parabola. And what I mean by the common sense method is most textbooks, authors, and instructors teach a method to graph a parabola that requires the student to make a huge leap of faith. It usually involves something called completing the square, and transforming a quadratic equation into vertex form, which we'll talk about in a moment, or a little bit actually. Um, but it doesn't really give you a great idea as to why you do that. Also, it's a huge amount of memorization, I think, and so what I'm trying to do here is get you to kind of have a common sense approach to graphing a parabola. The first thing about this common sense approach is just to note that all parabolas are U-shaped and they open wider and wider as time goes on. In other words, you have some parabolas that look like this, and as time goes on, in other words, as we keep moving to the right here, this parabola keeps moving to the right as well. It keeps opening wider and wider. It doesn't go straight up and down, in other words. And also we have those parabolas that look like this. They're upside down. And those also continue to open wider and wider and wider. In other words, a parabola never goes vertical. It always slowly lurches to wider and wider. The second thing I want to note is that if a parabola continues to widen out, in other words, we just said, it just gets wider and wider and wider, that it must eventually hit the vertical axis or the y-axis. And I put the vertical axis in parentheses here because you're not always going to be using a variable y for your vertical variable. So it must eventually hit the y-axis because it's just widening out. So even if the y-axis is way over here, eventually this gets wide enough to hit it. In fact, let's go ahead and say that it intersects the y-axis or the vertical axis at some height c. It could be at a height of 5, it could be at a height of negative 10, it could be at a height of 0. But at some point it hits the y-axis. The third thing that we all have to kind of agree with, and I'll actually bring up a side graph real quickly to show you what I'm talking about. But I'll state it here. As long as the vertex is not on the y-axis, then the parabola must reach this height of c at some other time as well. And we'll call this a symmetric point. Now, what do I mean by this last little bit? Suppose that I have a parabola and I know that it hits the y-axis at a height of negative 2. Let's just pretend. Well, then we know that either the parabola is doing this, or it's doing something like this, or it might be opening downward like this, or it might be opening upward the other direction. Oops, wasn't the best drawing there, but something like that. But in all of those cases, you see it hits that height of negative 2, curves down or curves up, and eventually comes back up to that height of negative 2. In other words, because it's U-shaped, if I reach this height at some point, I got to reach that height again later on. Same thing if it's U-shaped this way. If I reach this height at some point, at some other point I have to be at that height again. The only exception to this rule is if we have the vertex on the y-axis. Something like this. In this case, you're not reaching this height of -2 again because that's the lowest point on your parabola. Or if it was the highest point on your parabola, it looked like that. But the fact is that it's a point on your parabola that is actually the vertex, and so it's never going to reach that height again. There's no symmetric point. So it turns out that these types of parabolas, the ones that exist on the y-axis, are always of the form y equals ax squared plus k. And those are actually very quick and easy to graph because, as we've seen in a previous lecture, k just shifts the graph up or down, and the a, the coefficient of x squared, it controls whether it's flipped and whether it's stretched or compressed. And notice we don't have an x term in here, so no, just single little x term, and that's the indication that we're going to exist on the y-axis. Once we have an x term in our equation, instead of just an x squared, that we have an x squared and an x, then we know it's been shifted by some amount left or right. But the easiest way to graph it at that point is using the method that I'm teaching right now. All right. Now, halfway between these two symmetric points is going to be the vertex, the lowest low or the highest high, and also the axis of symmetry. And so if you look at, actually, let's create a new example here. If we just create a quick example, let's pretend that we know we hit the x-axis at a height of -3, let's pretend, and then we find out that we end up being that height of -3 way over here. Halfway between whatever this x value is, and let's say it's a -10, halfway between -10 and 0 will be our axis of symmetry. And that axis of symmetry is a vertical line. Remember, equations of vertical lines are x equals. That's x equals, in this case, -5. So I happen to know the vertex exists at x equals -5. And now all I have to do, to build this quadratic, or to build this parabola, I would need the overriding quadratic equation. I'm just going to plug in that x equals -5 into the quadratic equation they gave me to find out the corresponding y coordinate for the vertex. And that's what I'm saying here in step 5. Plug this x value into the original equation to find the y value for the vertex. At that point, you have two symmetric points and the vertex. You can graph the parabola. So let's go ahead and try this out. This is just a method I taught in the previous lecture. So we'll try this out with just a single equation, just to get the feel of it. So let's go ahead and graph 0.6x squared plus 0.6x minus 1.2. I know it's going to be parabolic because it's a second degree polynomial. So let me go ahead and just give a set of axes here. I have no idea right now where the y-intercept is, but I'm just going to ask myself, since I know it's a parabola, I know it's got to hit the y-axis, so I'm just going to ask myself what the y-intercept is. And that means let x equal 0. Well, when x is 0, all the first two terms disappear, and the y-intercept turns out to be a -1.2. So I'm going to choose a different color for plotting this, actually in a different pen size as well. So -1.2 might occur right there. I'll label this as 0, -1.2. And then I'll go ahead and ask myself, when are we at that height again? Because that's the strength of this method, is that we know our parabola reached the height of -1.2, and because it's a U shape, it's got to reach that height again, unless this is a parabola which has a vertex on the y-axis, which it isn't. It isn't that type of parabola because we happen to have this middle term here. So to answer this question, we're going to go ahead and let y equal negative 1.2 in the original equation. And what's beautiful about this is when you do this, and you look at this and go, okay, well, I have a quadratic equation that I need to solve. I'm going to go ahead and add 1.2 to both sides to start solving. Something always happens. This always happens. This is not just a fluke in this situation. You get that 0 is equal to 0.6x squared plus 0.6x, and then nothing else, which is really nice because then to solve this quadratic equation, all I have to do is actually factor it. Both these terms have something in common. I can factor a 0.6 and an x out of both. I'll be left with an x plus 1. So the answer to this question, when are we at a height of negative 1.2? Well, I have two objects that are multiplying to be 0, means either the first object is 0 or the second object is 0, which implies that either x is equal to 0 or x is equal to a negative 1. So I'm at that height of negative 1.2 when I'm at 0, which I already wrote in there, or when I'm at x equals a negative 1, which I'll go ahead and write here. So this is x equals a negative 1, y equals a negative 1.2. So those are my symmetric points. Halfway in between must be my axis of symmetry. If I could draw this nicely, I would. So remember, the axis of symmetry is a vertical line, so the equation is x equals, and halfway between x equals 0 and x equals negative 1 is x equals a negative 1/2, or a negative 0.5 in this case, if you want to just use that. At this point, all we need to do is plug that in, the negative 1/2 or the negative 0.5, into the original equation to find what the corresponding y value for the vertex is. So let's go ahead and plug that in. Plugging this in, we get y is equal to 0.6 times a negative 0.5 squared plus 0.6 times a negative 0.5, and then finally minus 1.2. Since these are decimals, I'm just going to quickly grab a calculator here and go ahead and calculate this out. So I have a 0.6 times and a negative 0.5, although I don't need to put the negative in there. I'm just going to do it. Plus, actually, a positive times a negative, so minus 0.6 times 0.5 minus 1.2. So we get a negative 1.35. Pull that off to the side. Therefore, I know our vertex occurs at x equals a negative 0.5, y equals a negative 1.35, which is just slightly lower than these two purple points. So it's probably right about here. I'll point a little arrow at it and call that negative 0.5 comma negative 1.35, and now all I need to do is connect these dots. In reality, that's all you truly have to know how to do when you graph a parabola originally. That's all we did in my previous lecture. So that's the only review I'm going to give on this method, and from that point forward, or from this point forward, I'm going to go ahead and start talking about new things we can do to really get a great idea of what this graph looks like. So if you want to review this idea more, please go to my playlist and find the one that's titled Graphing Quadratic Equations. But at this point, there are a couple more things that we should be able to find when you're looking for graphing a parabola. The other things that are kind of important to find here would be the x-intercepts. So we're going to go ahead and now start to find more info, I guess. We already have the y-intercept. we already have symmetric points. We already have the axis of symmetry. So find x-intercepts if you can. So I'll say if possible. And before you find the x-intercepts, you can actually use the discriminant to determine if there are x-intercepts. In reality, that's the only new thing we're doing here. We're not really doing anything else that's going to be new. So the only other piece of information here is just to find the x-intercepts by using the discriminant first to determine the number of x-intercepts. And then if we do know we have x-intercepts, we'll go ahead and find them. Now recall what the discriminant is. Given a quadratic formula, quadratic equation of the form ax squared plus bx plus c is equal to 0, the discriminant is defined to be the b squared minus 4ac. And you should notice that b squared minus 4ac looks very familiar because it's from the quadratic formula. This was actually underneath the root in the quadratic formula, so a little arrow there. And remember what we said about this in a previous lecture, that if you find out that b squared minus 4ac is negative, then you have a negative underneath the radical, so your quadratic equation here only has non-real solutions. It has complex number solutions. So what's interesting about that is, maybe I should use a different graph or page for this. What's interesting about that is if we have x-intercepts, just remember the x-axis contains only real numbers. This is something that when I was a student, nobody really focused on telling me, but it's true. The x-axis and the y-axis really only contain real numbers. So if I want to find out when this parabola, maybe I should put -1, when this parabola is at a height of 0, or in other words, when I have x-intercepts, first of all, I'm going to let y be 0, and I'm going to try to solve this equation. Well, I could solve this equation by hopefully factoring, which it won't work in this case. And if factoring doesn't work, I'll jump right to the quadratic formula. But remember, the quadratic formula has 3 possibilities. And it all just, for returning answers, either it returns no real answer, so you have 2 complex numbered solutions, or it returns 1 real answer, or it returns 2 real answers. Here's a picture of each of these situations. No real solution would look like this. In other words, I'm not ever going to be at a height of 0. Or it could look like this, or like this, or like this. But the fact is that it will never hit the x-axis. Okay, those are examples of parabolas that do not hit the x-axis. Therefore, when you try to solve their corresponding equation here, when it's set to 0 because you want to know when the height is 0 or when we reach the x-axis, you won't get a solution. You'll get a complex number solution. And that actually happens when you end up when you end up finding the discriminant and the discriminant is negative. So this implies that b squared minus 4ac is negative. Now, another possibility is that you have 1 real solution. And remember in our discussion in the previous lecture about about the discriminant, and if the discriminant is equal to 0, that we had a solution to an equation like this, gave us 1 real solution, and we called it of multiplicity 2. An example of this would be something like, I don't know, let's just pretend that you were to solve a quadratic equation. You get -3 plus or minus the square root of, and you do a bunch of calculation in here, the b squared minus 4ac, and it turns out to be 0. Let's say it's all over 2. Well, notice that in this expression here, you get -3/2. There's no plus or minus. There's only 1 solution. So it does happen that if what's underneath the root is 0, then you only get one solution to your quadratic equation. Now, what does that look like as far as when you graph this? What does it mean? It means that when you only hit the x-axis once, right? Again, setting y to equal 0, we're asking ourselves, when are we hitting the x-axis? And if we only have one answer, that means we barely touch it right at that point, and then we bounce right off of it. Or we barely touch it at that point, we bounce right off of it. In either case, it's just that we hit it once and then it moves on. So that is the vertex, essentially. Which is actually a cool thing to remember, that if you only have one real solution, that will actually be the vertex. Because it has to be. You're saying that it hits the x-axis at a single point. If there's no symmetric point, it means that that point has to be the lowest or the highest point on the parabola. That's just an interesting side note. And then the most common type is two real solutions to a quadratic equation. Again, we're just asking ourselves, when is y 0 for this quadratic equation? Or in other words, when are we at the x-axis? If we have two real solutions to this quadratic equation here, it'll happen because b squared minus 4ac is positive. In other words, what we have underneath the radical is a positive number, so we can take the square root of it. So if we go back to our previous example here, I mean, obviously by the picture we've drawn, we know that we'll have two x-intercepts. But let's just pretend we didn't know that. So to find the x-intercepts, we're going to go ahead and first find a discriminant. I'll call that d. d is equal to b squared minus 4ac. Let me change the pen size here so that I'm not such a bulky pen size on there. So let's see, b squared, that's going to be 0.6 being squared. Remember, a is the coefficient of x squared, b is the coefficient of x, and c is this constant term. So b squared minus 4 times a, which is a 0.6, times c, which is negative 1.2. And I understand that this, when you're dealing with decimals, it's just much easier to actually go ahead and grab a calculator, so please do that. 0.6 squared minus 4 times 0.6 times a negative 1.2. We get a 3.24, so that's actually positive, which tells me that we will have two x-intercepts. So all right, implies two x-intercepts. Some people might ask, well, why do you go through all this trouble? Why don't you just find them? Because it's much faster actually to find out the discriminant. You're going to have to do it anyway. You're going to have to find out what b squared minus 4ac is anyway when you're finding the x-intercepts. But if you find b squared minus 4ac first to determine the number of x-intercepts, well, if you are lucky in that your b squared minus 4ac is negative, then you don't have any x-intercepts, so you don't have to go any further. You can stop at this point. But in this case, we actually do have x-intercepts. We have a couple of them. So let's go ahead and find them. They occur when y is equal to 0, or in other words, when we want to solve this equation. And the quadratic formula is just going to give us x is equal to the opposite of b plus or minus the square root of our discriminant all over 2a. Our discriminant we've already calculated, so we haven't wasted any time here. And the opposite of b is negative 0.6 plus or minus the square root of 3.24 all over twice a, so 2 times 0.6. At this point, I would probably grab a calculator, just because, again, we have a lot of decimals in here. And what I'm going to do is actually store this number so that I can use it. So I'll, yeah, I should. We'll store this number as alpha a. And you can go ahead and pause the video, rewind to see how I did that. Essentially, it's just me hitting the store button and I want to store it as a letter, so I hit alpha to access the letters, and I stored it as the letter A. And now I'll go ahead and calculate the values here. So I'll start a numerator, negative 0.6 plus the square root of alpha A. I'll close out the square root and close out the numerator. Now I'll divide by that denominator, which is 2 times 0.6. Notice my use of parentheses. Whenever you're doing a large numerator or a numerator that involves any type of multiple operations, and same thing with the denominator, you should enclose those in parentheses. So we get this 1 and so maybe I should highlight that on here. It's just odd. I stared at it for a moment, it just seemed wrong. But so this is at x equals 1, y equals 0. And now let's find the other x-intercept. The way we can do this using the graphing calculator is second entry, just to bring back our old entry, climb up here and replace that plus with a minus and a negative 2. Even though it doesn't look like it on my graph because I didn't really graph it properly. That's negative 2 comma 0 and that's 1 comma 0. Very nice. So let's go ahead and try to graph something from scratch here. In this case, I'll go ahead and find the y-intercept really quickly because I know that all parabolas will hit the y-axis. So you let x equal 0, you'll get that y is equal to 1. And now I'll ask myself, when is y equal to 1 again? In other words, I'm hoping that we hit that height of 1 at some other point as well. So let's go ahead and let y equal 1. We get that 1 is equal to x squared plus 2x plus 1. When you subtract 1 from both sides, you get the following. 0 is equal to x squared plus 2x. And both of those terms there actually have an x in common. So this tells me that we're at a height of 1 when x is equal to 0 or x is equal to a negative 2. At this point, I probably should start graphing it just to kind of get an idea of what this looks like. So I'll draw a set of axes really quickly. This is my x-axis, this is my y-axis. And I said that we're at a height of 1 when x is 0. So let me use a different color to denote that. That's the height of 1 when x is 0. And then I also said that we're at a height of 1 when x is a negative 2. So here's a negative 1, negative 2. So we're at a height of 1 when x is a negative 2. Halfway in between those 2 points will be the axis of symmetry. So I'll go ahead and draw that in there really quickly. It's a vertical line, so that's of the form x equals, and halfway between x equals 0 and x equals negative 2 is x equals negative 1. And now all I need to do is plug this into the original equation to find out what the y value for that vertex is. So let's see, we have 1 minus 2 plus 1, which is going to be 0. I'll plot that in there. So it tells me that when x is negative 1, y is 0, so it's right here. I can already see right now that I'm only going to hit the x-axis once. But let's just see what happens when we try to find the x-intercepts here. But I can easily see I'm only going to hit the x-axis once because that's the vertex. But let's pretend that you just are not savvy enough to notice that. So let's find the x-intercepts, which means that we're going to first find the discriminant to see if we have x-intercepts, even though I know we have them. B squared is going to be 4 minus 4 times a times c. That gives me 0. So the discriminant 0 means I only have one x-intercept. I actually see it, that x-intercept is at -1, 0. You could also have used the quadratic formula to determine that that's the x-intercept by letting y equal 0. But there you have it. So discriminant, again, very nice. Had I waited until the last moment to graph this and used the discriminant to determine the to help out with the number of x-intercepts, I would have known before even graphing that I only had one x-intercept. Now let's go ahead and try something a little bit different here. Not very much so. We're going to go ahead and graph this quadratic equation. We'll start by finding the y-intercept. Like we know all parabolas at the y-axis, so you just let x equal 0. We find that it occurs at y equals 1. I might as well just go ahead and graph that right now. X equals 0, y equals 1. We'll pretend that's right there. And now I'm going to go ahead and ask, when are we at y equals 1 again? Because I want to know where the symmetric point is. So we'll let y equal 1 in our equation and see what the corresponding values for x are. We'll subtract 1 from both sides to get 3x squared minus x is equal to 0. Both those terms on the right hand side have x in common, so I'll factor that out. I'm left with a 3x minus 1. So this tells me that I am at a height of 0 when, or I'm sorry, I'm at a height of 1 when x is equal to 0 or x is equal to 1/3. So let's just pretend that this is x equals 1/3. I'm at a height of 1 when x is equal to 1/3. This is 0, 1. Halfway between those 2 points will be my axis of symmetry. Remember, the axis of symmetry is a vertical line, so that's of the form x equals. Halfway between 0 and 1/3 is basically half of 1/3, which is 1/6. Just multiply that denominator by 2. And at this point, you can plug this x value into your equation to find the y value for the vertex. So we'll go ahead and do that. So let's see here. That would be 3 over 36 minus 6 over 36 plus 36 over 36. Really, I'm just finding common denominators here. That'd be negative 3 over 36 plus 36 over 36, or in other words, 33 over 36. Both these numbers are divisible by 3. That's 11/12. So it's at a height of 11/12 is when I have my vertex. So let's see. 11/12 is just slightly below a height of 1, so it's somewhere right around here. Connect up these points to finish your graph. I'll connect them in a different color here. It looks something like this. Now, I don't even want to bother trying to find the x-intercepts because I know just by looking at this it doesn't have any. So I'm not going to bother. Had you tried, by the way, early on, let's say you save the graphing to last, and that's why, by the way, I graph as I go along through a problem. So I don't, if somebody's asking me for the x-intercepts as well, I could see, before I even need to find them, I could see that I don't have x-intercepts. But if you're the type that needs to do all the math before you graph, then when you try to find the discriminant here, which is b squared minus 4ac, you'll see b squared is going to be a negative 1 being squared minus 4 times a times c. That'll be 1 minus 12, or in other words, negative 11, which is less than 0. So I know that when I let y equal 0 to find the x-intercepts, I'm going to solve an equation where the discriminant is 0 or negative, which means that what's underneath my square root in the quadratic formula is going to be negative. Or in other words, I don't have a real number solution. I just have two complex number solutions, which don't exist on the x-axis. Now, I suppose that I would be very, very, wrong if I did not introduce another form of the of a parabola. It's called the vertex form of a parabola, and it is one that is cited in textbooks all over the place. Oh, use the vertex form of a parabola. Use the vertex form of a parabola. But in reality, nobody hands you the vertex form of a parabola. They hand you the standard form of a quadratic equation. So something like y equals 1.2x squared plus 0.1x minus 3 or something. That's how they hand things to you. They don't hand them in a pretty factored form. So this theorem, vertex form for a parabola, is only useful in textbooks. How's that? It's not super useful elsewhere. That's why I don't really concentrate on teaching it. But this is the vertex form of the parabola. Y equals a times the quantity x minus h being squared plus k. If somebody hands you, is nice enough to hand you a quadratic equation in this format, then you know the vertex is going to be at h comma k, and you happen to know that it opens up if a is positive, down if a is negative. But you still have to find some points, and you still have to find x-intercepts and fun stuff like that. So I'm going to do an example, but this is the one that a lot of students really cling to and hope that they get. And I'm letting you know right now that you shouldn't be given these. These are not styles of formulas that you should be given. You should be given more challenging things. So let's go ahead and graph a negative 1/2 times the quantity x plus 4 being squared minus 3. What this tells me is that the vertex for this, it's going to be a parabola because it is quadratic. If you multiply this out, it will have an x squared term. The vertex, according to that formula, will be not at positive 4, but at negative 4 and then negative 3. It's always the opposite of that number. So it's at x equals negative 4, y equals negative 3. So if I start graphing this, people think, oh man, this is much better. Well, it's much better because somebody did work for you. But it's not always going to be like that. So I'll go back 1, 2, 3, 4, and down 1, 2, 3. There's my vertex. And I happen to know that it's opening down because that's negative. So let's go ahead and find, we have to find at least 1 point here. So let's go ahead and maybe even 2 points. Let's go ahead and let x equal, so that we can find 2 other points. The easiest points to find are actually the neighboring points. So let's let x equal negative 5. If x is equal to a negative 5, then y is equal to negative 1/2 times negative 5 plus 4 squared minus 3, which is actually a very nice point because negative 5 plus 4 is a negative 1, and when you square that, it becomes a positive 1. So this is just going to be a negative 1/2 minus 3 here. So that means you're about at a height of negative 3.5, somewhere around here. And if you were to let x equal, to find another point, let's see, our center point here is at x equals negative 4. So let's let x equal negative 3. In other words, go 1 point to the right. This is what I call the wiggle. You wiggle 1 to the left and wiggle 1 to the right to find some extra points. When you do this, you'll find out that it's a symmetric point. So negative 3 plus 4 squared minus 3. Negative 3 plus 4 is 1. Being squared is just 1. So this turns into a negative 1/2 minus 3 again. So we're actually at a negative 3.5. And now you can connect these dots. It would be nice to find the y-intercept. To find the y-intercept, you let x be 0. So you scroll down quite a bit here. Hopefully you eventually hit the y-axis. It's a parabola, so you will eventually. If you let x equal 0, you'll find that y is equal to a negative 1/2 times 4 squared minus 3. That's 16 times a negative 1/2, or in other words, a negative 8 minus 3, which is a negative 11. So I know that this happens at x equals 0, y equals a negative 11. And you know the axis of symmetry, by the way, is along the center line. And that center line occurs where the parabola, or I'm sorry, where the vertex of the parabola is at x equals negative 4. Now, I have to say that this is very mathy. You can see all the math that occurs here, but it's also not the best. People don't know, well, why is it that the vertex is at negative 4 comma negative 3? And, I'm just doing what I'm told to do, is what people generally do, rather than having a common sense approach to say, well, listen, I know that all parabolas will hit a y-axis. So when are they going to be at that same height again, halfway in between the vertex? Here you're just following some type of formula or recipe, really. There really isn't much else to graphing using the vertex form of a parabola. It's just memorizing that formula, unfortunately. Of course, it could happen that somebody asks you to find the x-intercepts as well. Well, you can see with this graph, there are no x-intercepts, but it could happen that you do have a parabola given to you as a quadratic equation in vertex form that does have a couple x-intercepts, and so to find the values for those x-intercepts, you would still let y equals 0 and solve. All right, that's enough for this.